Hello everyone and welcome to the third session of our After Hours sessions. Today I want to speak about three topics which we went through and talked about in our lectures, and I'm going to begin with the reachable space, which is related to controllability. So in class we considered an LTI system, so we have a system defined by A, B, and C, which are constant matrices. And we saw in class that specifically for LTI systems, the system or the pair AB is controllable if and only if the controllability matrix, denoted by Q, has full rank or has rank n, where n is the dimension of the system. Let's define the reachable space. The reachable space of our system is composed of all states which are reachable from initial condition 0, so from the origin, by using some controller. So specifically, it's just a set of all vectors in Rn such that there exists some time t and some input u such that x is equal to this integral over here, which is of course the general solution of an LTI system for initial condition 0, because then the homogeneous part simply cancels. So we have a theorem. The theorem states that the reachable space is spanned by the columns of the controllability matrix. So basically this means that I can compute the controllability matrix using A and B, take out only the linearly independent columns, and they will span the reachable space. Now, how does this theorem actually relate to controllability? If the rank is equal to n, Q spans the entire space. So the reachable space is the entire space. And this is exactly the meaning of controllability. We can reach any point in space. If the rank is less than n, Q does not span the entire space. There will be some areas in space which are unreachable for the system, and this is exactly lack of controllability. So this theorem goes hand in hand with what we know about controllability. I'm going to skip the proof because these sessions are supposed to be fun, but the proof is here if you want to go over it, and if you have questions, just email me. Now, another thing we learned in class, that for LTI systems, the pair AB is not controllable if and only if there exists an eigenrow R of A, like a left eigenrow of A, that is orthogonal to B. So R times B is equal to 0. So if this holds, we know the system is not controllable. And we also know that if R times A equal to lambda R, then R times A to the K is lambda to the K R. Now we have another theorem which states that if there exists an eigenrow R of A such that R times B is equal to 0, then the input has no effect in the direction of R. Moreover, R is perpendicular to the reachable space. And again, I'm skipping the proof. I do suggest going over it. This proof is really simple, but in any case, basically what we do here is that we show that if R times B is equal to 0, then R times Q is equal also to 0. This actually means that R, in the sense of vector spaces or just geometry, is perpendicular to Q, and since Q spans the reachable space, R is perpendicular to the reachable space. Okay, now let's see how this comes into fruition in an example. Let's see how this works physically and geometrically. So consider a circuit with 3 capacitors with the same capacity C and 2 resistors R, which are of the same resistance. Now the states are the voltages across each of the three capacitors. So V1, V2, and V3 will be our axes. Our input is a single current source connected only to the middle capacitor. Now, if we let R and C be 1, then we will obtain the following system. I'm not going to go over the derivation, but you should know how to derive this. In any case, here you see that B is 0, 1, 0. This corresponds to our input only going into V2. Okay, now let's check for controllability. So we have A times B, 1 minus 2, 1. A squared times B is just A times B multiplied by A from the left. So I can take 1 minus 1, 1 and just multiply it by A. We don't actually need to compute the A squared each time. And the controllability matrix is what we see over here. And now, if we denote the columns of Q by Q1, Q2, and Q3, we can see that Q3 is minus 3 times Q2. So we have 1 times minus 3 is minus 3, minus 2 times minus 3 is 6, and again 1 and minus 3. This means that these two columns are linearly dependent, and the rank, therefore, of Q is 2, which is less than 3. The system is not controllable. Now, the first theorem states that the reachable space is obtained by the span of Q. So basically, we take two linearly independent columns of Q, in this case 0, 1, 0, and 1 minus 2, 1. And this is the reachable space. So the reachable space are all vectors in R3 such that they are a linear combination of these two vectors. We can also verify easily that if we let R be 1, 0, minus 1, then R times Q is the 0 vector. Basically, this R is exactly the left eigenvector of A, which corresponds to a non-controllable eigenvalue. And our second theorem states that 1. The input has no effect in the 1, 0, minus 1 direction. And 2, this direction is completely perpendicular or orthogonal to the reachable space. So this is a picture, but we also have the code. So if we go all the way up here, okay, so this is the reachable space for our system. So the axes are V1, V2, V3, our voltages, and basically what we see here, this plane is basically all combination of voltages obtainable by our system or by our input, to be more precise. So using our input, the voltages V1, V2, and V3 can only be somewhere on this plane. And note that we have this red arrow. This is exactly the direction 1, 0, minus 1, which is indeed perpendicular to this plane, and we cannot affect the system in this direction. This means that if we want to simultaneously increase the voltage of the first capacitor and decrease the voltage of the third capacitor by the same amount, we cannot do it. We cannot move the system in this direction. Okay, so this is the reachable space. Now we also talked about Kalman decomposition. These will relate in a moment. So I remind you that we saw in class that if a system is not controllable, and specifically if the system, the rank of Q is n1, which is less than n, then we can take the n1 linearly independent columns of Q, put them in a matrix, then take another n minus n1 column vectors, put them in a matrix such that this matrix T inverse is 1 n by n and invertible. So we can always choose P1 up to Pn minus n1 to be all linearly independent and linearly independent to these Q's. Then, if we do a change of variables, if we let Z, our new variable, be T times X, we obtain a new system with a new A matrix given by TA T inverse and a new B matrix given by TB, such that the system is decomposed into controllable and uncontrollable parts. This means that we have a subsystem A11, which is an N1 by N1 matrix. We have B1, which will also have N1 rows, such that A11 and B1 is controllable and A22 and 0 clearly is not controllable. Moreover, and in some sense this is actually more important, our new variables are split into controllable variables. These are the first N1 entries of Z, and non-controllable variables, which are the last N minus N1 entries of Z. Now, a common mistake is to think that if we have some uncontrollable eigenvalues, say lambda 1 up to lambda n1, and then the rest are uncontrollable eigenvalues, then the first n1 state variables are controllable and the rest are not controllable. And this is actually not true. It is true about the Z system. The first n1 Z variables are controllable and the rest are not, but it's not true about the X system. Basically, what this means is that our controllable and uncontrollable variables are not exactly the original system variables, but they are some linear combination of the system variables. And we will see that in a moment. So in our first example, we obtained this Q, and we saw that the rank is 2 and not 3. Now, in order to construct T inverse, we will just take two linearly independent columns of Q. So we take 0, 1, 0 and 1 minus 2, 1. So we put them in a matrix, and then we need to find another column which is linearly independent to these two, and 1, 0 minus 1 does the trick. Clearly, it's linearly independent with 0, 1, 0 and with 1 minus 2 and 1. Okay, now the inverse of T inverse is T, which is given here. Now let's do the decomposition. So TA T inverse gives us this new matrix, and T times B gives us this new matrix. Now, be careful here. N1 in this case is 2 because it's the rank of Q. This means our subsystem, which is controllable, should be 2 by 2. So this is A11 in this case, and don't be confused by the general form being 1 and then zeros. N1 is 2 in this case, so B1 is the first two entries of B. Okay, so we have B1, we have A11, and let's confirm that indeed this is controllable. So A11 times B1 is just 0, 1, and then the controllability matrix for the subsystem is B1, A11 times B1, which is clearly invertible, just the identity matrix, so the rank is full, and these two are controllable. But what can we actually control? So this is the important part here. If we compute Z explicitly, so Z is T times X, we obtain that Z1 is the sum of the voltages. Z2 is the sum of the first and the third over 2, and Z3 is the difference between the first voltage and the last voltage. Now, what we obtain, I remind you, N1 is 2, so the first two variables are controllable and the last one is not controllable. This means that we can, using our input, we can control the sum of the voltages. We can control the sum of the first and the third voltages. and we cannot control the difference between the first and the third voltages. This actually emphasizes the fact that we cannot control all three voltages separately. So we can control the sum and we can control these two, and you can think of it as, you know, being two equations in three unknowns. It's not solvable, so we cannot have one equation for each. So we cannot control each one, and we already know the system is not controllable. Clearly, if the system is completely controllable, then each voltage can be controlled. Now, what is the physical meaning of the fact that we cannot control this? Let's go back to our actual system. Sorry. Yes. The third variable is z dot 3 equal to 0 times z1 plus 0 times z2 plus 0 times z3 plus 0 times u. Okay, so if we actually write this down, we have z dot equal to 0, so this means z3 is a constant. If z3 is a constant, this means the difference v1 minus v3 is always constant, and this goes hand in hand with the fact that we cannot control it. It always remains the same. It's always 10. If it's always 10, I cannot change it. So it's not controllable. And if we actually plot the reachable space in the Z system, everything becomes really, really nice. So let's go to our code. And basically everything becomes perpendicular because of this diagonalization process we did. So we have an axis for Z1, an axis for Z2. These are the controllable variables. So the reachable space is just the Z1, Z2 plane. It's really nice and flat. And the perpendicular direction is just the third direction. Now, what is this third direction? Note that half x1 minus x3 is half the vector 1, 0, minus 1 times x, which is exactly the r we saw earlier, which was the perpendicular direction. So everything works. Now, there is a deeper physical point here. So note that while we cannot control x1 or x3 individually, we can control their sum. This means that uncontrollability isn't a failure of each component. It's a physical constraint on the shape of the system. Because v1 minus v3 is always constant, it's like a physical constraint. And no matter what I put into the system, using my specific input, which is always an input in v2, this always has to hold. So the shape of the system, the combination of the voltages, always needs to be such that this is constant. So it's a deep physical constraint which does not allow me, in this case, to move the system in a specific direction. So just by knowing A and B, we really analyzed things with quite deep, meaningful physical and geometrical meaning, which is quite nice. Moving on to the third thing we went over in class, which is the Dyadic decomposition. So first of all, just a reminder, if A is diagonalizable, we can write it as U lambda V. Lambda is simply a diagonal matrix of A's eigenvalues. U is composed of the eigenvectors of A, and V is the inverse of U, but it's also composed of the eigenrows of A, of the left eigenvalues of A. Now, if we denote by gamma 1 up to gamma n the columns of Cu, and by beta 1 transpose up to beta n transpose the rows of Vb, then we saw in class that the transfer function is given by the following sum. Now, The PBH theorem implies that only controllable and observable modes of the system appear in G. Why? The PBH theorem implies that if lambda I is not a controllable mode, not a controllable eigenvalue, then beta I transpose is equal to 0. If lambda I is not observable, then gamma I is equal to 0. So if either one mode is not observable or not controllable, then the entire term will cancel. So only if an eigenvalue is both controllable and observable, it will actually appear here. Now let's use this nice decomposition for active noise control. So consider a system with 3 speakers. We have a left speaker, a central speaker, and a right speaker. But we only have a single power amplifier. So we can only have one plug-in, one input into one of these speakers. Now our idea is to decide which physical ports to use to ensure the system can perform a specific task given a limited power budget. Okay, so let's see what we mean here. So the dynamical system is the same as in the previous example, the homogeneous part. Now for the input, we consider 3 different scenarios. So we have plug into the left speaker, in which case B1 is X00, plug into the central speaker, in which case B2 is 0x0, and plug into the third speaker, in which case B is 00x, and x is basically the amplitude, like the amount of volume or how loud is the volume we want to put to amplify through the speaker. Now for the listener, we again have 4 cases. So either listener is sitting in front of the left, central, or the right speaker. So we have C left, C central, and C right. And we have another option where the listener is experiencing the whole room. So in this case, CW whole is 1, 1, 1. So these are all the combinations, are the listener, the left, center, right, and everything, like the entire whole room. Okay. Now computing the eigenvalues and eigenvectors, we first have lambda 1 equal to 0. We have eigenvector 1, 1, 1, and left eigenvector, third, third, and third. This is called the mono mode of the system. Why? The speakers are projecting a mono signal where the sound waves from all 3 sources add up consecutively everywhere in the room. So they are all projecting in the same phase, so it's constructive. This is called a mono mode. For lambda 2 equal to -1, we have an eigenvector 1, 0, -1, and left eigenvector half, 0, -half. This is called the stereo mode. So basically the left and the right speaker, they work simultaneously, but with an offset, like with a different phase. So this gives a feeling in the room of, one speaker going this way and the other that way, and the waves, the phase is such that the music is sort of moving in the room. So this is called a stereo mode. This is basically the meaning of stereo. The air is shuffled from left to right, and we hear it as stereo. Now we have the third mode, which is eigenvalue -3, eigenvector 1, -2, 1, left eigenvector 6, -3rd, and 6th. And this is the interference mode. So imagine the left and right cones, speakers push with some phase, and then the center is working with just the opposite phase. So the speakers are sort of fighting with each other, and the air is very, very compressed, and basically the phases interfere with each other instead of being constructive like in the mono case. Now the U matrix is composed of the eigenvectors. So each eigenvector we put as a column in U. V is composed by the row eigenvectors. We put them as rows. Now, I remind you, for G, we need to compute CV and VB because the columns of CU go into G and the rows of VB go into G as well. Now here we have 3 types of B's and 4 types of C's, so we just compute all the case. So this is what we have, VB1, VB2, VB3, so we have column vector each time, and just for the first input I denote the entries as beta 11, beta 21, beta 31, and so on. So basically the 1 to the right indicates inputs, and then the first index indicates just the row. Now, without even computing anything, we can see right away that for the second input, the system is not controllable. Because beta 22 has some 0 in it, and if beta 22 has some 0 in it, then the corresponding mode will cancel in G. We will talk deeply about this in a moment. Note that if we create a matrix for the betas, because this is one column, this is another column, this is the third column, we have that beta ij is x times v ij. This is v, and the first element is 1 over 3, and the b11 is x times 1 over 3, and this works for all the entries. So beta ij is just x vj. Now we do the similar thing for the outputs. Here each time we get a row vector. So we have the first case CL, so 111, and this is gamma L1, gamma L2, gamma L3, and so on. And again, we can immediately see that for the second case, for the central speaker, the system is not observable because we have a 0 over here. And for the fourth case, when we listen to the whole room, we have 2 zeros actually, and in this case also not observable. Now, what is the meaning of these gammas and the betas? So the betas are like the valves at the inputs, and gammas are like microphones at the outputs. So specifically, beta ij represents the input authority over mod I using speaker J. Basically, it tells us how much the J speaker excites the ith natural shape of the system. So natural shape as in mono, stereo, and so on. So specifically in this case, beta 22 was 0. This means that the central speaker cannot control the second mode, which was stereo. And this makes sense because stereo is this play between the left and right speakers. So if we only put music through the central speaker, it makes sense that we cannot control the stereo. Now, beta 21 was x over 2, and this means that the leftmost speaker, because we have 1 here, which corresponds to the first, the leftmost speaker, excites the second mode, the stereo mode, by x over 2. So the amount of excitation is proportional to x. So if we put in an amplitude, a volume amplitude x, then the stereo will hit us with volume x over 2. Now the gamma ki's represent the sensor sensitivity or the listener sensitivity to mode I at location k. It tells us how much the ith mode shows up at the kth output. Now, even if a mode is vibrating violently, if the corresponding gamma is 0, the listener at that point hears nothing. So if the listener is at the central speaker and only the stereo mode is working, the listener won't hear anything because the stereo mode works with the left and the right speaker. So it makes sense. So here, as I just said, gamma C2 is equal to 0. Because if we are listening to the second speaker, the central speaker, the stereo mode, which is the second mode, is invisible to us. We have some sort of phase cancellation. Now, Gamma W1 is equal to 3. This means that if we listen to all speakers simultaneously, because we have the W here, we are extremely sensitive to the mono mode, which is the first mode, as we see here. Why we are extremely sensitive, there's nothing special about the number 3, but in comparison with all the other numbers here, 1, -1, 2, 3 is the largest. That's why we say we are the most sensitive to this mono mode. Now, gamma W2 is equal to 0. This means that if we listen to all the speakers simultaneously, to the whole room, the stereo mode cancels out. I know it might not be intuitive, but you can think of just the phases of the left and the right speakers just cancel each other. Now, the transfer function due to some input J and some output I is given here. So we need to choose one input and one output, and we immediately get our transfer function for this case. Now, since we are working with 3 modes, it's natural to have the following definition. So the total gain of the system for mode L due to input J and output I is given here by RL lambda IL beta transpose LJ. What does this mean? This is obviously a matrix, and each entry in the matrix basically tells us how much input J affects output I. Now, if the absolute value of RL is large, the mode is very loud in the output. So if the stereo mode is very, very numerically big, this means it's very felt in the output for the listener. If RL is 0, the mode does not appear. The listener can't even hear it. If an entry of RL is greater than 0, this means the input U and output Y are in phase for this specific mode. So if we increase our amplitude for the input, the listener hears an increase in volume. If some entry of RL is negative, then it's the opposite. If we increase our amplitude for the input, the output, the listener will hear a decrease in volume. It sounds not opposed to natural intuitive, but it can happen due to just phase cancellations. Now let's set up a goal. Let's actually compute something. We want to design a system that produces a stereo effect. So stereo is the second mode. We care about L equal to 2. And we want an audible intensity of at least T equal to 10 decibels, dB. So we want to have a stereo effect, and we want to actually be able to listen to it loud enough with 10 decibels. Now we ask ourselves which physical speaker should be wired to the amplifier, that's one, and we want to know the minimum required input amplitude X necessary to influence the speaker above a detectable level, above T basically. And we also have a maximal amplitude, which is natural. We don't have an infinite amount of volume. Basically, we want the size of R2 to be larger than T, which is 10 dB. And we know that R2 is gamma I2 beta 2J. So basically we have a matrix, and we want to find an entry of this matrix which will be larger than 10 for a minimal X. So basically we have this problem. We want to minimize this term over X, J, and I such that this term is larger than 10. So basically what we want to do, since we want to minimize over X, we will take the entry which is larger independently of X. So first of all, what we do, we just compute the stereo influence matrix, which is R2. So we compute each term, we just plug in i's and j's and we compute. Obviously we use this over here and we use these values over here, and we get a 4 by 3 matrix because we have 4 outputs and 3 inputs. So let's see what is the meaning of the matrix. So basically this means that if the listener is next to the left speaker, and if we plug in the center speaker, the listener will hear nothing, and so on. Basically this means that first of all, for the listener to hear anything, the speaker we use must be the left or the right, because the center speaker gives us nothing no matter where we stand, which is interesting. And if the listener listens to the left speaker, the input must be either left or right. And if the listener is listening to the right speaker, the input must again be left or right. And it doesn't really matter because the amplitude, as you can see, is the same numbers. But basically for our cause, since we want to minimize over x, let's say this is x over 2 and this was twice x, we would obviously choose twice x, because then x can be less than it would be here. But in this case, all the non-zero entries are the same, and basically we want x over 2 to be larger than 10, and basically the maximal value for x is 20, so we can only reach exactly this value of 10. So we must use the maximal total amplitude to produce an intensity of t equal to 10 decibels. Now, let's go back to the code. Basically what this code does, you choose the mode and it computes the matrix we just saw. So for L equal to 2, this is the matrix, as you can see. Basically, here the rows are the listener at L, C, R, W, speaker 1, 2, and 3. So this is what we had. This is for x equal to 1, and we can see these entries are the same height, so which is half, and all the other entries are 0. It's basically the matrix we just saw. It's this matrix, only, visualized. Now, what's interesting, let's say we want to have a mono system. We can see here that first of all, no matter where we stand and no matter which speaker we choose, we hear something, and that's good. But we can actually see that if the listener is at W, at the hall, listens to all the speakers, the influence of the 3 speakers, first of all, it's the same influence throughout, and it's much bigger than when we're standing at the left, center, or right speakers. Actually, it's 3 times larger. So it's interesting. The math actually works because we saw earlier that the impact of the first mode for listener at W is very large. It was 3 as compared to 1 and -1 and so on. So basically, if we are in a studio and we have lots of inputs and we have microphone and different locations, when we do audio for an album or something, we can actually play with these matrices. We can actually have these matrices in front of our eyes to choose the correct input that will give us a sufficient volume for the microphone. So it's quite nice. And we can say that even though the notion of the Dyadic Decomposition is very mathematical and not that interesting, we can actually use it to have some interesting and nice real-world applications. And that's it for today.